All right, so let's talk about Chapter 5, Part 2. Verifying trigonometric identities. So when you have an identity that is in question, in other words, we're not sure if it's an identity or not, the process to verify that identity is to show that each side is the same expression. And there's several different tactics we're going to use to make that happen. But the goal is to show the equation is the same. So the only definition that's new is that verification. Show that both sides of an equation are the same expression. So let's begin here with this identity. And even though we're asked to verify them, I'm not going to throw one at you that's not an identity, because that's a particularly cruel tactic. So only actual identities are going to be up for verification. So here, we've got a couple things going on. I see some Pythagorean. So when I see something squared, I want you to think Pythagorean. And probably rewriting both the numerator and the denominator is a good strategy here. So let's start with the Pythagorean identity, the primary Pythagorean identity. We want something that includes the tangent. The tangent is the sine over the cosine. So if I divide every term by cosine squared x, the result will include the tangent squared x. And 1 over the cosine is the secant. So I can rewrite that numerator as secant squared x. And then that denominator, if I subtract sine squared x from each side, I get this result, and I see that I can rewrite that denominator as cosine squared x. So the resulting expression is going to be, and also, I didn't mention this earlier, but when we're attacking a trigonometric identity, you should always simplify the more complex side. You see how the left side is more complex in this case algebraically. So that's why I chose to attack the left side instead of the right. And they are both candidates for simplification, but in this case, the right was easier. So I'm going to rewrite this as secant squared x over cosine squared x. And we're trying to show that that's equal to secant to the 4th power of x. So, and I see how to do that right away because one over cosine is secant. Hey, Leslie. Hello. So secant x equals 1 over cosine x. So I can rewrite this second factor on the left as secant squared x. And now it's just algebra. Secant to the 4th power of x equals secant to the 4th power of x. And we have verified. So when you get the same expression on each side of the equation, we have verified that identity. Try to get this all up here simultaneous. Okay, so that's a pretty simple example. And one thing I want to caution you about, I've worked these problems a lot of different times. And in some cases, I remember, the fastest way to do it. And so you'll have a very efficient strategy like this. I have no missteps, no wrong paths, but the potential for that is very high in working these problems. So if you try something, if you use a certain identity and it doesn't simplify the expression, be prepared to go back to a previous step and try again. I've had to do that many times. All right. So now let's talk about this one, which is 2 minus cosine squared x equals 1 plus sine squared x. This one's kind of trivial if you do this trick. I'll subtract 1 from each side. I get 1 minus cosine squared x equals sine squared x. So you can do that, perfectly legitimate, to use any algebraic step that you see would give you an advantage. And don't think you're going to have to pull your punches on these problems. Give it. If you see a very quick and easy way to solve it, use it. Here we're going to use the Pythagorean theorem for that, the Pythagorean identity for that left side. And if I subtract cosine squared x from each side, I'll get this. And I see that this expression and this expression are the same. So I can substitute this equivalent expression for it. And I get right away verified identity. Again, that was an efficient path. There are many inefficient paths that would arrive you at the right answer, but not as quickly. Okay, so let's do a tricky one here. Combining fractions. So this term, combining fractions, means we need to get a common denominator, and it's clearly going to be the case that we need that on the right. So -2 cotangent x, this is our target. Now this is what we want to get to with that right side. So we're going to multiply each by the other's denominator, top and bottom. And give myself the maximum room there. Times 1 plus cosine x over 1 plus cosine x. The result of this step is going to be a common denominator. -2 cotangent x equals sine x times 1 minus cosine x over 1 minus cosine squared x. So what I'm doing there is, this is a difference of squares. See how it becomes 1 minus cosine squared x when I multiply those together. And then over here on the rightmost term, I get this. And once again, difference of squares creates 1 minus cosine squared x. So we have a common denominator. -2 cotangent x equals sine x. And I'm going to hold off on distributing that for just a second. Combining the fractions first. Because they have a common denominator, we can do that. Remember that a over c minus b over c equals a minus b over c. So we're rewriting it in that way. Now I see a simplification I can make. I can factor out a sine and turn that bottom term into a single. Well, let's distribute and see what cancels first. All right, so I've got -2, I like the black better for this. -2 cotangent x equals sine x minus sine x cosine x. And the negative is going to distribute to both terms here. So that's minus sine x minus sine x cosine x. And it's all over 1 minus cosine x, but I'm going to rewrite that as well on this step. You remember that sine squared x plus cosine squared x equals 1. If I subtract cosine squared x, I can see that another way to say that is sine squared x. So we're getting there, believe it or not. Sine x and minus sine x will cancel. So our next step is going to look like this. -2 cotangent x equals -2 sine x cosine x over sine squared x. So another way to write sine squared x is sine x times sine x. And here you see 1 power of the sine will cancel. -2 cotangent x equals -2 cosine over the sine is the cotangent of x. So we did it. Verified. I'll try to get this up here. Yeah, okay, it all fits. Just barely, but it all fits. Okay. So let's move on to example 3, which is verifying by multiplying. What they mean by that is, you see how this denominator is, if I multiply it by its conjugate, it'll be a Pythagorean kind of a deal. So if you have a 2-term denominator like this and it's -1, some trig function -1, if we find that conjugate and multiply top and bottom by that conjugate, we're trying to get to here, we'll have a Pythagorean situation that we can simplify. All right. So we've got sine of x times secant x plus 1 over difference of squares again, secant squared x minus 1. And we're trying to show that that's equal to that expression. Okay, so remember that the secant x is 1 over the cosine x. So I can rewrite this as sine times 1 over cosine x, which is sine x over cosine x. And then for that denominator, remember that sine squared x plus cosine squared x equals 1. And if I manipulate this algebraically, if I divide everything by cosine squared of x, I'll get sine over cosine is the tangent squared x. Plus 1 equals the secant squared x. Then if I subtract 1 from each side, I get tangent squared x equals secant squared x minus 1. So I can replace that denominator with the tangent squared of x. And we're still trying to get to here. Slowly but surely simplifying this left side. All right. So, and I think this is probably a little counterintuitive. I'm going to rewrite the sine over cosine as the tangent of x. So that's all I'm doing on this step. But the next step, it's a little counterintuitive because it's not what we usually do when you're simplifying. Usually you want as few terms as possible. We're always trying to reduce the number of terms. But here I see on the right side 2 terms. So let's make this left side 2 terms as well. And we can use that property I've used previously in reverse. In other words, a plus b over c equals a over c plus b over c. Let me change the color of that so it's more clear that that's something a property that I'm using and not an actual step. So the result is going to be the tangent of x over the tangent squared x plus the sine of x over the tangent squared x. And again, we're still trying to get to this cotangent x plus cosine x, cotangent x. But we're almost there. I see the pathway. So this is going to cancel to be 1 over the tangent x. And over here, so this is sine of x divided by, remember the tangent is the sine over the cosine. So cotangent x plus cosine x cotangent x is what we're trying to get to. So 1 over the tangent x is also the cotangent of x. And we see that we've got that first term to match. So that's a victory. Now, if we get the second term to match, we're good to go. Remember, keep, change, flip. When you divide by a fraction, we're going to do that. So we keep, we change to multiplication, and we flip. So what you've got here is 1 power of sine is going to cancel. So this is going to cancel out one of the powers of sine in the denominator. And so we're going to get cotangent x plus cosine x times cosine x divided by sine of x. So 1 power of the sine in the denominator was canceled out by this sign, which gives us this. Still trying to get to here, but we're almost there now. So finally, cotangent x plus cosine x, and another way to say cosine over the sine is cotangent x, and we have done it. So this is the same as the right side of the equation, and we have verified that the original relationship is an identity. In other words, it's something that's always true. As algebraically, we simplified the left and made it into the right. And I'll try to get all this up here at once. This doesn't really like to cooperate. Not quite. So I'll show the top bit here, and I'll show the bottom bit. And this will all be on the notes I'll attach as well. So that's example 3. Example 4 is verifying by factoring. So sometimes factoring is a good strategy. We'll do that. I see on the left side here, it is the obviously more complex side. So we'll take that and make it look like the right. Factoring is clearly our good strategy, and we're going to factor out a GCF, the greatest common factor. I see that everything on the left contains at least 1 power of a cosine and a tangent. So I can factor out cosine x, tangent x, and the result is going to be, and we're dealing with that left side, we're trying to make it into sine of x. So secant squared x is the only factor left in the first term, and tangent squared x is the only factor left in the second term. And the reason why that's good for us is I see we could play around with the Pythagorean identity. We can play around with the Pythagorean identity. Oops. I don't know how I got on the wrong page. Like the wrong page by a mile. Okay, here we are. Use the Pythagorean identity to rewrite this in parentheses here. So I've got sine squared x plus cosine squared x equals 1. I need something with the secant, so I'll divide everything by cosine squared x. So I've got sine over the cosine, which is the tangent squared x, plus 1 equals the secant squared x. So I can replace secant squared x with tangent squared x plus 1. Why would that be important? Well, because tangent squared x minus tangent squared x is going to be 0. It's going to simplify that expression. Cosine x, tangent x times tangent squared x plus 1 minus tangent squared x equals sine x, and tangent squared x and minus tangent squared x cancel. So you're left with just 1, and I'm going to rewrite the tangent as the sine x over the cosine x. Everything in here just becomes 1. And the cosine x's cancel. So sine x times 1 is sine x. And we have done it, verified that identity. So, and also, I want to remind you guys what I had mentioned earlier, which is that I've worked these problems a lot. I've got strategies here that I can look at. So I'm taking the right path right away, but that won't always be the case. Be prepared to make a wrong turn somewhere, have to go back and start from a certain point and move forward again. That's something you'll definitely have to do at some point. All right, example 5. Verify identities by working each side separately. These are the trickiest of all. So think about it like this. If I'm spinning a plate on one finger, that's hard, but it's not impossible. But spinning a plate on 2 hands simultaneously is exponentially more difficult. And so that's what we're going to find here. We're going to have to kind of work independently and try to arrive at the same expression. That will definitely be a challenge. So if I look at the right side here, I see that I have a denominator that looks like I could multiply by its conjugate and get something that simplifies pretty well. Using the Pythagorean identity. So I'm going to multiply top and bottom by the conjugate on the right. On the left, I think breaking it up into 2 terms is a good strategy again. So let's see what happens when we do that. So I've got tangent x over tangent x plus 1 over tangent x. So that's going to be 1 plus cotangent x. So this is going to be 2 minus cosecant squared x times 1 plus cotangent x over, and then this is a difference of squares. So that's 1 minus cotangent squared x. And there's an interesting step I can do here. I can divide both sides by 1 plus cotangent x. And I'm going to get 1 on the left, which is the simplest possible expression, at least from my point of view. And over here, that will cancel. So that'll get rid of one big headache for us. And we got 2 minus cosecant squared x over 1 minus cotangent squared x. I'm trying to keep my color scheme consistent here. Close enough. So I see some Pythagorean deals going on there. So let's think about cotangent. Sine squared x plus cosine squared x equals 1. We need the cotangent, which is the cosine over the sine. So if I divide everything by sine squared x, I'll get 1 plus cotangent squared x equals 1 over sign is the cosecant squared x. So if I subtract 1 from each side, I get cotangent squared x equals cosecant squared x minus 1. Will that help us? Yeah, I think it will. I think, in fact, it'll get us exactly where we need to be. Because if I plug this in for this, it's going to simplify out and be something that'll clearly be equal to 1. So let's, on the next step, let's write, I'm going to shrink all this so that we have room for our next step while we're looking at that one. All right, so 1 equals 2 minus cosecant squared x, and then we're going to plug in cosecant squared x minus 1 here. So 1 equals 2 minus cosecant squared x over 1 minus cosecant squared x plus 1. The negative distributes there. So 1 plus 1 is 2. Same expression, top and bottom. 1 equals 1. We have done it. So I'll start here with the top and show you the bottom. There's literally 1,000 different strategies we could have used there. This is just one. And it's not even exactly in keeping with what they said, work them separately. Well, here I divided both sides by something, so that kind of violated that premise, but whatever. Don't pull your punches with these problems. You know, sometimes I say it's instructive to use this certain technique, even though it's not the most efficient way, because, you know, we really want to learn that new technique. Well, with these problems, that's not as big of a priority. I'm a lot more concerned about whether you can get there by any means necessary than I am about using whatever technique is recommended. All right, going on to example. Well, let's talk about this first. So this is actually a worthwhile strategy guide for these. Start with the more complicated side as a general guideline. These are guidelines, not rules. So there will always be exceptions to these. Reciprocal, quotient, Pythagorean, and other basic trig IDs. You remember I attached the list of those to the 5-part 1 assignment. Use algebraic operations such as combining fractions, rewriting fractions as sums or differences, multiplying expressions, or factoring expressions. You saw me do all that on those problems. Convert a denominator if it's 1 plus or minus u or u plus or minus 1 to a single term by using its conjugate. You saw me do that many times. Work each side separately. So we did a little bit of that in the previous example. And if no other strategy presents itself, convert the entire expression to sine and cosine. So this last one, and I wind up here a lot actually with these, because if I'm working one for the first time, sometimes the path to a solution is not obvious, and this is sort of like the catch-all for these. If you convert it into sine and cosine, the relationships will be more obvious. Okay, so determining whether an equation is an identity with a graphing calculator. I wanted to show you this one real quick because it's kind of neat. So when you're working with a graphing calculator, you can use that to see if there is an identical relationship on the left and the right by seeing if the graph matches. So what you'll do is plug in the left side into y1, and watch how I plug this in here because it's a little different. Make sure you put the numerator in parentheses and the denominator. Cosecant is 1 divided by the sine of x, and then times the secant, which is 1 divided by the cosine of x. Oops. There we go. Then close the denominator. Just making sure I put that in there right, because that's tricky. Okay, yes, I think I did. And we're going to see if that's equal to the tangent of x. So we're basically seeing if the graphs match. And I'll make the second line fat so it's more obvious. Here's the first line. And it's a pretty complex expression, so it's going to challenge our little TI processor. Sure looks like the tangent to me, but we'll wait and make our verdict. Oh, yeah. So you see how those lines are an exact match? So we can say now graphically, this is an identity. So the task in this problem was to see if it was a good candidate, and then I do it algebraically. I'm not going to do that. You've seen enough of those. Let's go on to the next one, because this one is a little bit of a different scenario. So if I plug these expressions in, first of all, I have cosine of x to the third power in the numerator minus sine of x to the third power. Close the numerator. And then in the denominator, I have cosine x minus sine of x. Close the denominator. And on the right side, I have cosine of x squared minus sine of x squared. And again, I'll make the second line a fatter line so we can see more clearly what's going on. Otherwise, it just overwrites and it looks like one single line. So again, we are challenging the little TI processor here. All right, and we see clearly those graphs do not overlap. And so this is not an identity in this case. All right, so the task for homework is page 324, 4, 8, and 12. Hope you guys have a good day.